So good morning to everyone, and thanks a lot for organizing this nice conference in Italy in some sense. So I'm the second one of the Paris group, Italian Paris group. And actually I will talk about these short minimal codes and related combinatorial structure. These results are contained in some papers which are joint work with Gianni Alfarano, Alessandro Neri, Alberto Ravagnani, and Daniele Bartoli. You will see at the end some references. So I thank Helena to give a nice introduction on coding theory, actually, so I can avoid to give details on that. But let me recall some basic definition. I mean, our setup is to consider linear codes, so subspaces of F2 to the n. And in this vector space F2 to the n, we consider the M metric. Not the only one that we can consider, but for this talk, this is the metric that we have. So we have the M in support of a code word, that is an element of the code, which is the set of coordinates in which the code word is non-zero. We can take the cardinality of this set, which is the weight, the M in weight of a code word, and we can take the minimum among the non-zero code word, which is the minimum weight, which is also the minimum M in distance for linear codes. So this is very classical, and as Elena mentioned, we want to have a code with nice parameters and so on. But this is not the focus of this talk, because actually we are considering different things I will tell you why later. So we are considering minimal code words and minimal codes. So a minimal code word is a non-zero code word such that any other code word which has a support contained in the support of this code word C is a scalar multiple. So we cannot have is minimal with respect to with the support. And a code is called minimal if every non-zero code word of C is minimal. So these codes were this notion of minimality were considered first for some application to the coding process. But I will say that the main interest now, for application is in secret sharing schemes based on codes introduced by Massey in 1994. I will not talk about this application, unfortunately, because there is no time, but this is a possible application of these objects. And let me give now some very trivial example of minimal codes. Minimal code, every simplex code SQK is minimal. What is a simplex code is essentially the code that you obtain by taking a generator matrix, which has columns given by all non-zero vectors of Q to the K up to a scalar multiple. So this is the length, this is the dimension, and these codes reveals to be constant weight, so they have just one weight, one non-zero weight, and this is Q to the K minus 1. And this is essentially, this last property is essentially the one that gives you that the code is minimal, because you can prove it actually. But if you look at this example, which is of course special because it's in the binary case, then this should be evident. So this is the simplex code over F2 of dimension 3. This is a generator matrix of this code. Of course, they are defined up to equivalence. So these are all the code words, and these are the support of the code words. And you can see that they are all of the same cardinality. So of course, if one is contained into the other, it should be equal. So this is the property that gives you that the code is minimal. And the natural question is, how can we can construct other examples? And this is I would say still an open question. There are a lot of construction, but they are not optimal in some sense. I will tell you why. And at the beginning, I will say that many constructions were done by adding one row here, one row to the generator matrix of a simplex code, and try to figure out the properties of this row. This is the idea behind many constructions here, the so-called CF construction. On the other side, of this talk, there are objects which are in combinatorial structure in finite projective geometry. So defining projective geometry of dimension k minus 1 and order q is the set of points which are non-zero vector up to a scalar multiple. And in this finite projective geometry, we can consider hyperplanes, which are subspaces of the codimension 1. And inside this setting, you can consider the so-called blocking sets, which are sets of points such that the intersection with any hyperplane is different from 0. If you add the condition, you can have a stronger condition. I mean, you can define strong blocking set to be set of points such that the intersection with every hyperplane span linearly the hyperplane itself. This is a stronger condition, and these are the so-called strong blocking set. A trivial example of strong blocking set is, of course, the wall projective space, because actually here the intersection of the projective space with the hyperplane is the hyperplane itself, so it spans linearly the hyperplane. These two objects, so minimal codes and strong blocking sets, are essentially the same object, and the correspondence was observed first in November 2019, independently by us, I mean by Zanira, me, and Alessandro, and by Tang and other authors, almost at the same days, 2019. And it states that equivalence classes of projective minimal codes of dimension k in Q to the n are the same, are in correspondence, are in one-to-one correspondence with equivalence classes of strong blocking sets in PGK minus 1Q. I don't have time to state this correspondence explicitly, let's say, but I will explain it with an example, with a small example. The correspondence is is well known in coding theory. The correspondence between codes and points in PGK minus 1Q is well known, and it works as this: you choose a generator matrix. Here we choose the generator matrix of the simplex code that we considered before, and you consider columns. I mean, here you consider lines because I took the transpose space. And each column, you make each column correspond to a point in the projective space. And so each code corresponds to a set of points. And then, of course, there are other properties. And if you do this, then your simplex code corresponds to the set of all points of the projective space. So it corresponds to the projective space. So this is the so-called Fano plane. Fano plane, and this is the strong blocking set, and the simplex code is a minimal code. So you see the correspondence. A natural question then is the following. I mean, since if you think about the geometrical meaning of strong blocking set, you realize immediately that if you have a strong blocking set and you add a point, then the set is still a strong blocking set. So an interesting question is, how short can a strong blocking set be? Okay, let's start with an example. I mean, if you are in F2 to the 6, and you want to, the question is, how short can a minimal code can be, or equivalently, how small can a strong blocking set can be? You realize quite easily, this is an homework, I mean, if you want to do it, that you can take out a point, but not more. I mean, this is essentially due to the fact that you want that the intersection with lines should span the line. So if you take out 2 points, then there is a line that is not intersection. So the shortest length of a minimal code of dimension 3 over F2 is 6. And this is also proved in general by this theorem. I mean, we proved a lower bound on the length of a minimal code of dimension k over q, and this is this distance. So q plus 1 times k minus 1. So let me underline that this lower bound is linear in k. And this is actually an improvement of a former result by Bote's packet that was proved only for small k compared to q. The question becomes more complicated if you think about other dimension. I mean, here with the Fano plane is very easy. I mean, it's also over 2. But if you start to consider codes of dimension 4, then it starts to become more complicated to see it from a general point of view. And as an example, I mean, here we are considering PG3-2, and you can prove that the shortest length of a minimal code of dimension 4 is 9. And this is also good with the bound proof before. But the natural question is, how can we do to construct short codes in general for all dimension and all Q? In this, we have a very nice result, I mean, which is an improvement of a former result by Siamenager, Gérard Cohen, and others, which tells you that the best that you can hope is to have a length which is linear in K. You know, and you know that these exist. I mean, you know that the length of the shortest minimal code of dimension K is linear in K with this coefficient. But the problem is that this construction is this result is not constructive. It does not provide you an explicit construction of minimal codes of short length. But of course, it tells you that this is possible. It is possible to do. So let me conclude with some construction that we know. I mean, this slide is full, sorry, but I want to give just an idea of the possible construction that we have at the moment. So the first one is was presented in different ways by different authors, and is what we call the tetrahedron. So you take k points in general position in pk minus 1, and you take the lines through these 2 points, and the union of these lines is a minimal code of dimension. I mean, gives you a minimal code of dimension k, a length which is quadratic in k. I mean, you have this binomial. It is quadratic. This is I would say, a very easy idea, I mean, to construct form blocking sets, but you can get something slightly shorter by some smarter ideas, say, which are presented in this paper, but still quadratic. Then, on the other side, you have some short construction, which are linear in K, so, but they are constructed by taking some tangent lines to the rational normal curve. So for this construction, you need K to be smooth. You have this condition, K. And weakness in some sense, because you would like to have a short construction, all K. One, from a coding theoretical point of view, at least. And there are slightly shorter construction by many authors. I pointed some of them. I didn't forget someone. And more recently, with Daniele Bartoli, we proved that we found an asymptotically good family of codes, of minimal codes. Asymptotically good family means exactly what we know, what we want about the length should be linear in K, and also the minimum distance, but you will see next slide. Obvious in some sense. So we got some good construction of short code by concatenating asymptotically good AG code with simplex codes. There are two problems in that. This is nice, I mean, but there are two problems. And the first one is that this construction does not work for any K, for infinitely many K, but not all of them. And the coefficient of K is quadratic in Q. So this is the weakness in some sense. So there is still room for improvements in construction. As I mentioned, whenever you get a construction which is linear, whose length is linear in K, then you automatically have that the minimum distance is linear in K, too, by this lower bound. And so any construction with length linear yields explicit asymptotically, which is results in general in coding. So some open questions are, how can we find other infinite families of short minimal codes? It would be interesting to have a geometric insight of our construction, because I mean, still something to understand in it. And then, of course, the lower bound that we gave at the beginning is not sharp, so maybe you can improve this bound. And probably also the minimum distance in general can be improved. And another problem can be to consider upper bounds on the length of reduced minimal code. That essentially means how many points you have to take to be sure to have code. And that's all. These are some references, and thank you very much for the attention.